Okay, so welcome to our first section. We're going to be in this transition online. So we're going to talk about sections 4.1 and 4.3. Now, the reason I'm combining these sections, which this is going to be video one about it, is that these two sections are very linked to each other. It's sort of hard to talk about 4.1 without talking about 4.3 at some level. So because of those reasons, I'm combining them. So what is this talking about, these two sections? Well, the focus is on what are called extreme values. That's your maximums and minimums. So you could think, well, why do we want to talk about this? And I mean, there's the, obvious answer of, well, your math teacher tells you we're going to talk about it, so we're going to talk about it. But that's not really a satisfying answer. Another answer would be that there's a lot of application for maximums and minimums. For example, you want to maximize your profits often, because if you could get such money, but you know that that's not the most money you can get, you're going to try to get more money by maximizing profits or minimizing costs. And so there are these real world examples on why people would want to look at this idea of maximums and minimums. Okay, so now that we know what this section is going to be starting to talk about, we need to talk about, well, what is a maximum and minimum? Is there a more, I guess, math-like way of defining them? So we're going to define what we mean there when we talk about a maximum or minimum. So I'm going to take a number C. Let C be a number. And f a function. If I can spell. Then if you take its domain D, so the number, so remember that domain is just what x values you can put in. So then we're going to say f of C is an absolute maximum on D if you get this inequality. Well, you have the function value, so your y value for that x value of C, and you have f of x, which is the y value for all the other points. And if it's a maximum, well, the inequality that we'll want will go this way. It'll go this certain way so that a maximum should be larger than all the other stuff. So we can talk about that, and we can also talk about absolute minimum. And all you do is you flip the inequality, and this is for all x in the domain. So out of all possible x values, your absolute max is the one that has the absolute highest y value you can have, versus the absolute min is the absolute lowest y value. And that's all good, but it doesn't quite capture whenever we think of a maximum as in a polynomial. You have the top of the hill that you get from your graph, right? You want to say that this is some sort of maximum, and same with this, as well as this being some sort of minimum. But on this interval, on the domain, it's not going to be the absolute maximum or minimum. So we need some sort of adjustment to this. So talking about it, we can talk about what are known as local extreme values. Okay, so a local maximum value is one where you still have that inequality, but it's for all the x values near C. So in a way, it almost looks like that sort of like limit type thing that we were talking about back in chapter 2, where it's talking about on some maybe open interval near C, you have it being an absolute. So for example, this graph, this is going to be an absolute max because if we draw this little open area, and I'll highlight on that part, you see that the highest y value is where we would want to say our maximum is. And it's just on that open interval, because if we try to extend that open interval to be the entire thing, this is no longer a maximum. But on that small little bit near C, it is. And similarly, you can define a local minimum. Where you just flip the inequality, and still for all x near C. And so now we have our definitions. What does that look like? Well, let's look at a graph to just really detail this difference between the absolute and local, because right now it's just sort of this language, this mathematical language with inequalities that may or may not make sense. So let's say I have this function, and I'll give scale to my x-axis. So let's say I have this function f that it's going to start up here, go down, not 2, go back up a little bit till 3, and then go back down very drastically till almost the x-axis at 4, and then come back up and end at 5, x equals 5. So here, if I want to look at the absolute maximum, I look, well, where is my highest y value? Now the way I drew it was not super great, but it looks like probably around f of 1 is my highest y value, so that's going to be my absolute max. It just so happens to be an endpoint. So you could say, is the other endpoint then our absolute min? But you look at where the lowest y value is, and it's not at the endpoint f of where it's at x equals 5, but x equals 4. And that's just by inspection. Where is my lowest y value? And then, so that's your absolute max, absolute min. You could start asking, well, what about my local maximums and minimums? Well, local minimums, you have to draw that open interval. If you want this f of 2, for example, that will be a local min, because small enough around it, there's going to be, it's all going to be greater than. It sort of has that valley at 2 comma f of 2. Similar with f of 4. And then you could say, well, is there any local maxes? And yes, by just looking, you have f of 3. Now you could say, well, like around 4.5, why is this y value not a local maximum or minimum? But notice, if you try to look on both the left and the right, no matter how small you get that interval, it will never be such that it's either the highest y value or the lowest y value. So that's why we're specifically looking for these sort of valleys and these peaks. And so that gives what our local and absolute extreme values, or extrema, are. So another interesting thing here that you see is this f of 4. You can have something be both a local minimum and absolute minimum. That does work. And the endpoints aren't necessarily always going to be the absolute highest or absolute lowest. Now, if you're having any questions on this, just remember that this is uploaded on YouTube, so you can always comment there and ask questions. Or you can always message me through Canvas. Okay. So right now we have a more qualitative approach to that. And before we move into the more quantitative, like how do we find these things in just a random function without a graph, we have two named theorems I'd like to talk about. First one is going to be about absolute extreme values. So the extreme value theorem, it says if f is continuous, on this closed interval, then f reaches its absolute maximum and minimum. So what that's saying is, if I give you a continuous function in a closed interval, and I ask you what is the absolute maximum or what's the absolute minimum, you can't say it does not exist, because it will by this theorem. And like you could have situations where there's multiple x values that give the same y value that just so happens to be the absolute maximum. However, you're just guaranteed that it at least happens once, that the absolute max is reached. Now, these hypotheses are important. You can have non-continuous functions like our old friend, the piecewise function. The absolute maximum here is where there's a hole, the jump in the graph. But it's never reaching that because there is the hole. So I couldn't ask you, okay, here's this function, where is it where is its absolute maximum? Because there's the hole there. So that one would not exist. Similarly, you could, if you draw a line with open endpoints, well, now this has neither an absolute maximum or a minimum, because it would be at those endpoints, but they're open. So they're not included. Now, the main point of this theorem is to include the sort of information like ability to ask you on a problem, okay, here's a function on this interval, what is its absolute maximum and minimum values? And we will get to ones like that later. Okay. The other theorem, and this one's going to be about local extreme values, is going to be called Fermat's theorem. What it says is, if f has a local extreme value at c, at f of c, and the derivative exists, then the derivative at c is equal to 0. So basically, if you have this function that you know it's differentiable everywhere, the derivative exists no matter what, so like polynomials, for example, and you know where the local maximum or minimum is, then its derivative with plugging in that number, that c in, is going to be 0. What this tells you is there can't, if you get a number such that its derivative is not equal to 0, but the derivative does exist, then it can't be a local maximum or minimum. For example, of the having a local extreme value, we know if you take the function x squared plus 1, then from algebra 2 you could say that 0, 1 is going to be a local minimum. So we could say, well, what's the derivative? Well, this is 2x. And then you plug in 0 and you get 0. So it does work out that if this derivative does exist, that Fermat's theorem, what Fermat's theorem says, does seem to work. Now, an interesting case is whenever you take something like f of x equals x cubed, this actually looks something like this. There is no local extreme value. It sort of like slightly stops, but then it keeps going. And you can get that, and then if you look at the derivative though of that, 3x squared by power rule, notice that f prime of 0 is 0, but there's no local extreme value there, which just further shows that this condition does not give you the local extreme value. But it's going to start helping us move in that direction. So we're going to define what are known as critical numbers. So a critical number or I'll abbreviate CN is an X value such that if we call it C, f prime of C is 0 or undefined. Now note there might be critical numbers that aren't maximums or minimums, but from Fermat's theorem, if you have a maximum or minimum, its X value needs to be a critical number. And this leads to what's called the first derivative test. What the first derivative test says is, well, remember, derivative is the slope of the tangent line. And so if something has positive slope, we would say it's increasing. So with that in mind, we say that if the derivative is greater than 0 for all the Rx values on an interval, then f is increasing on that interval. Similarly, we could talk about decreasing with our derivative being less than 0. So if the derivative is equal to 0 or undefined, we have a critical number. If you get greater than 0, you get increasing. Less than 0, you get decreasing. So how does this help with maximums and minimums? Well, anytime you have a local maximum, notice it's going from increasing to decreasing, and minimums going from decreasing to increasing. If you sort of draw them as lines, you get increasing looks like that, decreasing looks like that, which if you connect them, does look like a maximum. And then you have decreasing to increasing, connect looks like a minimum. So that sort of helps to get why this first derivative test is useful. So the steps are going to be, well, let's first find the critical numbers, then let's use the first derivative test to see what exactly is going on. Where do we have increasing, decreasing? Where do we have extreme values and all the fun stuff? Okay, so let's do an example. So let's say I have 3x to the fourth minus 4x cubed minus 12x squared plus 5. If I want to find intervals of increasing and decreasing, as well as the local extreme values, first derivative test says, well, let's find the derivative first. That way we can find critical numbers. Okay, by power rule, this is 12x cubed minus 12x squared minus 24x plus 0. So this is a polynomial, which means it's defined everywhere. So the only critical numbers happen when this is equal to 0. So you can pull 12x out and you get x squared minus x minus 2. And that's equal to 0. Further factoring gives you the x minus 2 and x plus 1. So just by using algebra, this gives our critical numbers x equals 0, x equals 2, and x equals -1 by setting each of those multiplication factors equal to 0. So how does that help? Well, that's our critical numbers. So if I'm going to order them. So first you have -1, then you have 0, then you have 2. So these are our critical numbers, and then I'm going to think about this in terms of a number line. And this first area over here is going to be for all my numbers that are less than -1. So what I'm going to do is I'm going to just pick one. So for example, x equals -2. Then I'm going to plug -2 in to f prime of x. And when I do that, I will get a negative number. You can verify that in your calculator. And I can do the same over here. I want to choose a number in between -1 and 0. So I can choose -1/2. And this time I'll get a positive number. Then over here, x equals 1. Plug it into the derivative, I get a negative number. And then lastly, x equals 3 over here, because I need a number greater than 2, and I get a positive number. Now, by picking this test point, because of the intermediate value theorem, you know that because these are the only points where it crosses 0, you can't have some negative numbers and some positive numbers in negative infinity to -1. You only have negative numbers because the derivative is a continuous function here. So what does that give? Well, we have this negative, which means decreasing, and then positive between -1 and 0 means increasing, and then negative and positive, decreasing, increasing. So how does that help us? Well, it tells us, first of all, what the negative infinity to -1, as well as 0 to 2, well, this is decreasing, our interval of decreasing, versus -1 to 0 and 2 to infinity. That's our interval of increasing. And then we can look at it and we see that it looks like now f of -1 is going to be a local minimum, as well as f of 2. Whereas f of 0 is a local max. So that's how these problems go. Now this problem could change a little bit if I say, well, let's just say on the interval, I want you to look at this function on a certain interval. So let's say that this is on the interval -1 to 1. What's the absolute extreme values? So you could start thinking, well, we haven't talked about this yet. Well, we talked about local extreme values. how do we do that? But if you think about those inequalities that we had, on the small interval around our local mins and local maxes, you have it being the smallest y value and the largest y value. So really, all we have to do, because that still doesn't account for the endpoints, is we need to check these endpoints. What is their y values? And we need to check all these local extreme values to see what their y values are. Now this one we don't have to check because f2 is not in our domain, is not in our range because 2 is not in the domain. So we could check f of -1. So 3 -1 to the 4th minus 4 -1 cubed minus 12 -1 squared plus 5. Or this is going to be 3 plus 4 minus 12 plus 5, or 0. And then we could also check f of 0, that's just going to be 5, and then f of 1, which is 3 1 to the 4th minus 4, 1 cubed minus 12 times 1 squared plus 5. Or that's going to give us -8. So then what that's telling us is our absolute extreme value will be, well, you have f of 5 being the absolute maximum it could be, and f of 1 is the absolute minimum it could be. So I did assign in Canvas it's called a check-in problem. Basically, it's in a Word doc format, and you can download it and then just submit in the Dropbox a picture of what your solution is. But it is just one similar to this, not with the absolute extreme values, but just with the regular finding the local extreme values. So that is the first derivative test. And just one more example before we stop this video is let's look at one that is a trig function. So sine x plus cosine x. First derivative test says take the derivative, and what you get is derivative of sine is cosine, derivative of cosine is negative sine. These are defined everywhere, so to find our critical numbers, we just set it equal to 0 and solve. So cosine x equals sine x. And on 0 to 2 pi, where does that happen? Well, we can divide by cosine x, and you get that 1 equals sine divided by cosine is tangent. And you can think, well, where does tangent x equal 1? Well, that's at, if you put it in a calculator, you'll get pi over 4. And then tangent repeats every integer multiple of pi. But within our domain, that's just pi over 4 and 5 pi over 4. Okay, so those are our critical values. Pi over 4, 5 pi over 4. Now we need to choose those test points. I'm going to choose 0, pi, and 2 pi. Nice easy numbers on the unit circle. And I'm just taking this 0, plugging it into the derivative. And so cosine of 0 is 1. Sine of 0 is 0. So I get 1, which is positive. Cosine of pi is -1. Sine of pi is 0. So we get negative. And then 2 pi is going to be the same as 0. So you get positive there. Giving increasing on, well, now it's only going to be 0 to pi over 4, union 5 pi over 4 to 2 pi, and decreasing on pi over 4 to 5 pi over 4. Any questions you can submit through the inbox on Canvas, or you can comment on this video. Please join in tomorrow. We'll talk about concavity test and second derivative test, as well as do more examples.